Hello, grade 12s. Welcome to Maths and Science 8. In this video, we are going to be doing question 2 of this paper. This is a very interesting question about arithmetic sequences and quadratic sequences. Let us get straight into it. 2.1 says the following is an arithmetic sequence, and we are given three terms. The first term is 1 minus p, the second term is 2p minus 3, and the third term is p plus 5. 2.1.1 says calculate the value of p. Well, this is easy because since this is an arithmetic sequence, we know that it must have a constant difference, which we usually symbolize as d. And this difference can be calculated from Tn minus Tn minus 1, meaning that this difference can be calculated from the second term minus the first term. And it must also be equal to the third term minus the second term. Therefore, as we can see, the second term is given by 2p minus 3, and the first term is given by 1 minus p. So this must be equal to the third term, which is given by p plus 5, minus the second term given by 2p minus 3. So now we can just simplify this equation and solve for p. And the first thing that we can do is removing the brackets. So let's take down 2p minus 3 as it is. And now let's transpose the negative into the bracket. So this will give us negative 1 and positive p. And then on this side, we can take down p plus 5, and then we do the same thing. So we'll get minus 2p plus 3. So now we see that we've got some like terms that we can combine. So 2p plus p is 3p. Minus 3 minus 1 is minus 4. And on this side, p minus 2p will give us minus p. And positive 5 plus 3 is going to give us positive 8. And now we can transpose negative p into the left-hand side. So this is going to give us 3p plus p, and we can transpose negative 4 into the right-hand side. So we'll have positive 8 plus 4. And now 3p plus p is 4p, and 8 plus 4 is 12. Therefore, we can divide by 4 on both sides of the equation to get that p is actually equal to 12 divided by 4, which is equal to 3. So this is the value of p. So p is equal to 3. Okay, so that's how you can answer 2.1.1. Now, let's take a look into 2.1.2. And we have 2.1.2a. And A says write down the value of the first term of the sequence. So this is very straightforward now that we know the value of P. So the first term is 1 minus P. But now from 2.1.1, we know that the value of P is 3. So it means that the first term is going to be 1 minus 3, which is equal to minus 2. Easy like that. And now let us look into 2.1.2b. So 2.1.2b says write down the value of the common difference. We can get the common difference by working out the difference of T2 and T1, or the difference between T3 and T2. And we had already simplified this in 2.1.1. For an example, if we want to use T2 minus T1, we can see that the difference is 3p minus 4. So this means that to find the difference we can use the 3p minus 4. So again, we know that the value of p is 3. So 3 multiplied by 3 is 9. And then you minus 4, you are going to get 5. And we can test whether or not this is correct by also checking whether T3 minus T2 would give us the same value. So T3 minus T2, as you can see, this gave us minus P plus 5. Even if we calculate the difference using this expression, we must still get the same answer. Again, remember that P is 3, so here we'll have minus 3 plus 8. And obviously, this is also equal to 5 as expected. So that is how you can do 2.1.2b. Okay, now let's see the last question on 2.1. So here the question is, explain why none of the numbers in this arithmetic sequence are perfect squares. All right, we can start by working out some of the values of the terms of this sequence. So the first term is negative 2, as we had already determined it in 2.1.2a. So our sequence has got the first term equal to negative 2. So what about the second term? Well, we know that the second term is 2p minus 3. So we can just substitute in the value of p, which we know to be 3. So 2 multiplied by 3 minus 3. This is going to give us 6 minus 3, and that will be equal to 3. Okay, so the second term is 3. In fact, remember that we know that the common difference is 5. So if we wanted to, we could have just simply worked this term out by simply adding 5 to negative 2. As you can see, negative 2 plus 5 is going to give us 3. Similarly, 3 plus 5 is going to give us 8, which is the third term. And likewise, if you want to go on to work out the fourth term, you can just simply add the common difference to 8. So 8 plus 5 is going to be 13. So the next term is 13 there. And likewise, you can go on to work out the fifth term. So that is going to be given by 13 plus 5, which is going to be equal to 18. So these are some of the terms of this arithmetic sequence. Let's refer to the question again. The question is, explain why none of the numbers in this arithmetic sequence are perfect squares. All right. So if you examine the terms of this sequence, you'll notice that besides negative 2, all the other terms either end with 3 or 8, 3 or 8, and this can go on and on. In fact, even if you were to work out the next term after 18, so 18 plus 5, that is going to be equal to 23. And guess what? It ends with 3. And what is the next term going to be? 28, right? Because 23 plus 5 is 28. And it's ending with what? With 8. So all of these terms here either end with 3 and 8, 3 and 8, 3 and 8. And now what you must know is that for a number to be a perfect square, so perfect squares, these are numbers that end in either 1, 4, 9, 6, 5, or 0. So since none of the numbers that we have in this sequence end with these numbers, none of them are perfect squares. You can think of a perfect square as a number you get if you take any number, let's say x, and you multiply it by itself. So it turns out that if you do this, the resulting number that you get will always either end with 1, 4, 9, 6, 5, or 0. So that is just a characteristic of perfect squares. In 2.2, we are told that the following sequence of numbers forms a quadratic sequence, and here they are. So 2.2.1 says the first difference of the above sequence also forms a sequence. So they say determine an expression for the general term of the first differences. So to answer 2.2.1, we definitely need to start off by working out the first differences of the sequence. So we have -3, -2, -3, -6, and we're also given -11. So let's work out the difference between the first two terms. So what is -2 minus 3? In fact, to make this process easy, I will use a calculator. So we need to find -2 minus -3. So this is equal to 1. So now let's find the difference between -3 and -2. So -3 minus -2 is going to give us -1. So that's -1. Now we need to work out the difference between these two terms. So in this case, we have negative, oops. So we have -6 minus -3, which is equal to -3. And last but not least, we are going to work out -11 minus -6. So that is equal to -5. Okay, this is the sequence that is formed by the first differences of these terms. So now remember that the question is asking us to determine an expression for the general term of what? Of the first differences. So we are going to take these first differences as a sequence. And of course, the type of a sequence that the first differences are making is an arithmetic sequence. That is because if we work out the second difference here, we will find that it's constant because this is a quadratic sequence. So -1 minus 1 is going to give us -2. -3 minus -1 is going to give us -2 as well. And then -5 minus -3 is also going to give us -2. So it means that the first differences form an arithmetic sequence with a constant difference of -2. And we know that the general equation of an arithmetic sequence is Tn is equal to A plus into n minus 1 multiplied by D. So we say that the first term is going to be 1, and then we just take down everything as it is, and then the constant difference is -2. And now we can just simplify the equation. So -2 into n, that will give us -2n, and then -2 into -1, that will just give us +2. And we can add up the like terms formed here. So that is 1 plus 2, which is equal to 3. So the expression for the general term of the first differences is Tn equal to 3 minus 2. So that is how you can answer 2.2.1. Now, moving on to 2.2.2. Here we are being asked to calculate the first difference between the 35th and 36th terms of the quadratic sequence. All right, so we want what? The first difference. Remember that we do know the general term of the first differences, but now we need to be careful with this question. Note that here, this is our first term of the sequence. This is the second term, this is the third term, this is the fourth term, and this is the fifth term. However, in the first differences, we have 1, 2, 3, 4 terms. For the first differences, you are going to have 4 terms, okay? And also note that this fourth term is between T4 and T5 of the quadratic sequence. And this is important because in order for you to be able to answer 2.2.3, you need to know which nth term in the first difference is going to be between the 35th and 36th terms of the quadratic sequence. So, based on this pattern I have just described, if between the fourth term and the fifth term we get a fourth term in the first differences, then it means that between the 35th and the 36th term, we are going to have the 35th term in the first differences. So what we are going to do is we are going to use the general term of the first differences that we have already derived. So in 2.2.3, we are going to take that and we are going to use it in order to evaluate this 35th term. So we are looking for the 35th term in the first differences. So this is simply going to be 3 into 2 multiplied by 35. And now we are going to see exactly what is the first difference between the 35th and 36th term. So we can just substitute this into our calculator. So we have 3 minus 2 into 35. So this is equal to -67. So it means that the difference between the 35th and 36th term is going to be equal to -67. So that is how you can answer 2.2.3. Oh, my bad, this is actually 2.2.2. And now we are gonna do 2.2.3. So 2.2.3 is determine an expression for the nth term of the quadratic sequence. Okay, so that is now going to be straightforward, right? Because we know that 2a is equal to the value of the first term of the second difference. And we also know that 3a plus b is equivalent to the first term of the first differences. So that is 1 in this case. And we also know that A plus B plus C is equal to -3, which is the first term of the quadratic. And now we can just simply solve these equations simultaneously. Firstly, we can see that if we divide by 2 on both sides of this equation, we are going to get A is equal to -1. And now we can substitute in this -1 into this equation. And this is going to give us 3 into -1 plus B equal to 1, meaning that -3 plus B is equal to 1. And then we can transpose -3 to the right-hand side. And this will give us 1 plus 3, which is equal to 4. So B is equal to 4. And now we can substitute in the values of A and B into this equation in order to solve for C. So -1 plus 4 is 3. Therefore, C is going to be equal to -3 minus 3, which is equal to -6. And we know that the general nth term of a quadratic equation is given by an squared plus bn plus c. So a is -1, so we'll have -n squared. B is 4, so we'll have 4n. And then C is -6, so we'll just write -6. So this is our nth term of this quadratic sequence, which then leads us to the last question, 2.2.4. And here we need to show that the sequence of numbers will never contain a positive term. So 2.2.4. So the idea is that you can treat this as a quadratic function. And remember that for quadratic functions, if the first term is negative here, it means that you are going to get a parabola that is concave down like this one. In order for us to prove that we cannot have a positive term for this quadratic sequence, we simply need to work out the turning point. The easiest way of working out a turning point of a quadratic function is by using calculus, and to be more specific, differentiation. So let's just simply work out the first derivative of this equation. So t prime of n, well, this is going to be equal to -2n plus 4, just by simply deriving this using the rules of differentiation. And now we can just set this to 0 in order for us to find the value of n for which the derivative is equal to 0. And remember that a derivative of a function can only be equal to 0 at the turning point. So there, t prime of n is equal to 0. So we can just transpose -2n into the left-hand side to get +2n. And then if we divide by 2 on both sides of the equation, we are going to get 4 over 2, which is equal to 2. All right, so what does this mean? This means that the turning point is at n equal to 2. The value of n there is 2. But now, if n is equal to 2, then what is the value of the term? So to do that, we will just simply substitute in 2 into our nth term. So we are going to get negative into 2 squared plus 4 multiplied by 2 minus 6. In fact, this calculation is trivial here because we already know what the second term is for this quadratic sequence. So there's actually no need for us to do this calculation because we already know that the second term is -2 as given here. So this is going to be equal to -2. You can check this in your calculator if you like. But now, what does this mean with regards to our question? So this means that the second term of this sequence is at the turning point of the graph, which is why now for all the terms that come after the second term, their values are all negative because as you can see, the graph is concave down. So as you are increasing the values of n, you are moving towards the negative direction of the graph. So this means that T2 is the maximum. And therefore, there are no positive terms in the sequence. So that is how you can answer 2.2.4. This question is just simply testing your knowledge of functions. If you have got any questions, you can ask me in the comment section. Otherwise, for any feedback that you would like to give me, feel free to leave that as a comment as well. And if you enjoyed the video, please like it and subscribe to the channel for more videos like this one. Thank you.